Three principles of constant rate of change. So this was the last question on your quiz, and my grader said that this was kind of the part we had the most difficulty. So we built up the three principles of constant rate of change, three mathematical things we said are equivalent to constant rate of change. And the first one was constant ratio, right? Corresponding changes in y and x maintain or keep a constant ratio. Delta y divided by delta x equals k. And then that value of k, that is the constant rate of change. That's the value of the constant rate of change. So this phrase, constant rate of change, it kind of has two meanings. It's an idea, right? It's a whole idea, but then it's also a value. And so to get that value, you take the ratio of the changes in your quantities. And if that ratio stays constant, you have constant rate of change. So the homework that you did for today, the hope was that you were applying this the whole way through. You kept returning to these principles, but because it's so new, we have to keep repeating it, and that's okay. So the second principle was that the change in one quantity is a constant multiple of the change in the other. So delta y equals k delta x. If you're ever given the change in x and you want the change in y, you know, constant rate of change is a matter of multiplying by the constant rate of change k. And then the last one was equal changes in one quantity results in consistent changes of the other quantity. So whenever x changes by 4, the resulting change in y will be consistent. It'll always be, say, a half, or it'll always be 100. And then when you change x by 20, whenever you change x by 20, you'll get the same change in y, whatever that is. Change in y is 5. Okay? So these are the three things. So as we're doing problems related to constant rate and linear functions, we're always looking for how does these one or more of these apply and help us to solve. Okay? So we'll do that with some of your homework questions. And then from there, we said that constant rate of change basically leads to a linear equation. If you have constant rate of change between two quantities, they're in a linear relationship. And so we use constant rate of change to build up the equation of the line. And the general principle of the equation of the line that we used was that the final y, which was like any y value on the line, was some initial y plus a change in y. More specifically, we came up with this right here. This is the form we came up with. Oh. One more try. Okay, so x1, y1 was a starting point. It was a given point. We knew this point x1, y1, and we started with what? A change in x to any arbitrary x value, so that final minus initial, change in x. The change in y was k times the change in x. That's our constant multiple reasoning, right? And then to get the new value of y, or the y value for any point on the line, we took the starting value of y, y1, and added the change in y. So we built this equation of a line using constant rate of change. So this was this idea of constant rate, this right here, constant rate of change, that delta y is k delta x. Right, so we're using number 2 up there to build that equation. Okay, and then we expanded that in class. And if we multiplied everything out, we saw that another way to write that was y equals kx plus b, or you're familiar with mx plus b. Just another form. So if we just do some arithmetic here, some algebra, we can get that kx plus b, which is like mx plus b. So this is like a point slope or point rate of change form. So this is point slope. And this is your slope intercept that you're more familiar with probably from past courses. But what's the deal with this point slope? It comes from our understanding of constant rate of change, right? We built that equation of the line from constant rate of change. So in all this long homework assignment you had, the hope was, I tried to encourage you, to be on the lookout to apply these principles, rather than something you learned, some kind of formula or method you learned in the past. We want to use our understanding to solve the questions, okay? So let's talk about some from the web work. Okay, so now that we've gone through that whole thing, we want to use that to talk about this. There we go. So keep this on the side, right? This is our foundation here. So the relationships of quantities P and Q could be y equals kx. Y equals kx. So now we're talking about how do you write the equation of the line, y equals kx. Could you write the equation of the line y equals kx? Always, sometimes, or never. Always, sometimes. So what we have is y equals kx plus b. So could it be kx? Could it be kx? Yeah. B is 0. If b is 0, you would have y equals kx. You still have the equation of a line. So always, sometimes, or never. Sometimes. If b wasn't 0, then that wouldn't be true. But if b was 0, that'd be true. So y equals kx. That's sometimes true. Okay? The graph relating quantities p and q on the xy plane is linear. Always, sometimes, never. It's always true, right? So we said when you have constant rate of change, you have a linear equation. It's always true. All right. If P changes by 5, Q changes by some multiple of 5 that varies depending on the starting value of P. So if P changes by 5, if we have a change, say a change in X of 5, then Q is going to change by some multiple of 5 that varies depending on where you start. Always, sometimes, or never? Never, because what is it saying? It's saying that the change in y is a constant multiple of the change in x. That doesn't change, right? If it's constant rate of change, k stays constant. This is trying to say that that multiple that you have, which in our case is k, is going to vary. Never true, right? Constant rate of change means k stays the same. Okay, the relationships between p and q could be represented by delta y equals k delta x. So if you have a constant rate of change, you could represent the relationship delta y equals k delta x. Always, sometimes, or never? Always. Constant rate of change means you have constant multiple reasoning right there. So it's always. Okay, so see how I'm drawing on this kind of this summary of what we've done in the last week or so. Green bar. Okay, got it. Next. So we'll go faster. How about the relationship of P and Q could be y equals kx plus b? Sometimes, always, or never? Y equals kx plus b. Always, right? This is mx. So every constant rate of change relationship can be represented kx plus b or mx plus b. Okay? What about this? Delta y equals k delta x plus b if b is not 0. B is not 0, then delta y equals k delta x plus a constant, a non-zero constant. Never true, because it would have to be 0 because of this, right? It's never true. The ratio of the change in P to the change in Q maintains the same value. Always true, constant ratio. If P increases, then Q increases. Okay, so some linear functions increase, some linear functions decrease. Constant rate of change could be increase or decrease. That's sometimes. And when the value of P is 0, the value of Q is 0 also. Okay, thinking constant rate of change. That's sometimes true. So you're thinking about a linear function. It could go through 0, 0, or it doesn't have to. All right, green bar. Let's see here. Green bar. Okay, so important stuff. So let's see, what else? 9, 10. These are ones that you had the most trouble with. Oh yeah, this one. So it's asking us to write the equation of this line. I think it can get bigger. So let's use this process. So you got to do it on the quiz, you got to do it on the test. So let's practice it again. So we want to write the equation of the line, and we want to use this building on this point slope form. Okay. So we have a point here. Let's start at this point here. 8, 4. Four, 8. Thank you. I was just checking you. Okay, and then if we want to write the equation of the line, then we don't want a specific point that we know. We want to think about just any point. I could have drawn that point anywhere, and so we arbitrarily call it x, y. And then when we find the value of y, that'll represent every y value on the line. Okay, so you're doing this on the quiz, you're doing this on the test, and we'll do it, and we did it last week. We'll do it again. So what was our first step? Here's our initial point, 4, 8. And our goal is to write an equation for every point on the line x, y, because we know. So how many points are on this line right now?
3,
4 points on the line, right? No, infinite number, an infinite number of points. That's what, when you look at a graph, that's what you're looking at. You're looking at all the points showing the relationship between, in this case, cups of tea drunk and hours of sleep obtained. Must be good tea, right? Okay, strong tea. So if we're starting at 4, 8 and we're going to end up at x, y, we're going to start with what? First step, change in x. Change in x from our starting point to x, y. So how do we represent that change in x? Step 1, delta x equals? Have we gotten this by now? X minus 4. So final value of the point, final value of x, initial value of x. X minus 4 is the change in x. Corresponding, so when x changes from 4 to x, the hours of sleep obtained goes down. How much does the hours of sleep change go down? And here we're going to use constant rate of change. Delta y equals k delta x. So we need k. How are we going to get k? We can get k from our constant ratio reasoning, right? That if your constant rate of change, which we have a line, it's going to be the change in y divided by the change in x. So we're going to use the 2 points that we have. Change in y is. So now to get this, now we're going to actually use these points that we know. Or we could use these two, that's fine. Let's use these two here. Okay, so change in y is negative 2.5. Change in x is 5. K is negative 1/2. So I used this down here to actually calculate k, these 2 points here. So now we're back to this, and we're solving for the change in y from 4, 8 to any arbitrary point on the line. And so we got our k was negative 1/2 times delta x, which is x minus 4. So that's our delta y. If you keep trying to avoid this thing that I'm doing, so stop and let's learn it this time. Okay, we've done it several times. You had to do it in your homework. You're responsible for it. First, start with a change in x from 4 to 8. That's x minus 4. Then corresponding change in y, k delta x, because we have constant rate of change. Right? That was number 2 over here. Okay, and then finally, number 3, step 3 is that the new value of y, this y equals our starting value of y, 8, plus however much y changed along the way. Should make sense. The y value that you started at, plus the change in y. So we get 8 plus negative 1/2 x minus 4. Except that I used y and x, and this all along this was q and s. So what, instead of y we should have s. And instead of x we should have q. So given this equation now, given any cups of tea, you get the resulting hours of sleep based on that relationship. Okay, again, and that's the old s plus change in s gives the new s. Yeah, so I should have done q s here instead of x and all these x's and y's. Should have been doing it q and s. So, but at the end I could just transfer. I know my y is my s and my x is my q. Any questions on that problem? Yes, sir.
Where'd you get the 2.5 from?
The 2.5. Okay, so in order to calculate the constant rate of change, I use these 2 points. So what's my change in y? Start at 4, I end at 1. So as x changes from 12 to 17, y is changing from 4 to 1.5. So that 4 to 1.5 is my negative 2.5 change in y, corresponding to a positive change of x of 5. Yeah?
Did you have to use those 2 points?
No. So you got 3 points to choose from. With constant rate of change, this is constant ratio. So any change in y with a corresponding change in x should give you negative 1/2. So it's fine. Yeah. Yeah. Another question.
You can get a different answer, right? There's different ways to do it.
Yes.
Okay. So there can be more.
But you're responsible for knowing this process where we use constant rate of change to build this form of the line. But yeah, so there are maybe 6 or 10 other ways that you could approach it to get it. Yeah.
Would you prefer us to leave it in that form, or should we multiply it off of that?
So for web work, it wouldn't matter. You could do any form that's right and get the right answer. So it depends on the instructions in the problem. So if they say leave it in point slope form, then you would leave it like this. If they say do the process and then find slope intercept form, then we'd multiply it out and get mx plus b. So just follow the instructions. And if it doesn't specify, and if there's more than one right answer, then there's more than one right answer. Yes, ma'am.
Sorry, is that a 2 right there? Or is s equals s squared, a squared now? Or is that next?
Okay, so where are you looking at?
That's right there. That
This?
Yeah, then that.
So what did I do? I changed y to what?
S.
Yep.
So it's the x.
And I
Oh, okay. I thought that was a number.
no, because this x and y means every and any point on this line. Then unfortunately through this whole thing I used x and y when I should have been using q and s, which are the actual variables. But it's the same in the end. Y is just s and x is just q. It's just a symbol. Okay. These are good questions. Any other questions? Okay. One last one having to do with so then the new topic that we had last time, this one about the restaurant. So let's go over this one. Okay, so this is about average speed. So we talked about average speed last time. And let's review this. So we have the distance d north of Mrs. Bess's restaurant in meters. So that's a well-defined variable given by the formula d equals 2t squared minus 7, where t represents the number of seconds since Bob began driving. So we've got our defined variables d and t. Okay, so determine the value of d when t equals 1 should be pretty easy. This formula does exactly that. Given a value of t, it gives you the corresponding value of d. So we could plug that in and we would get, I think, -5. And what does a negative value mean? That if this is d meters north of the restaurant, if he's -5, that means he's south. Okay? Average speed. So here we go. To find average speed, what did we say the meaning of average speed was? Can anyone remember the definition? Really important. What is the meaning of average speed? Yeah. Okay, that's how you calculate it. That's right. You're going to calculate the change in distance over change in time. That gives you average speed. But what's its meaning?
The constant rate that you have to go to get somewhere in the same amount of time.
Yeah. So that's what we emphasized last time. That an average speed is what? It's not adding up a bunch of speeds and dividing by the number of speed. Average is kind of an unfortunate choice for the name of it because that's what it makes you think, right? It makes you think about averaging test scores. Okay. But average speed is a constant speed to go the same distance in the same amount of time, right? And so that's what we want to calculate here. So from t equals 3 to t equals 5, I wanted white space here. Let's see. So let's just put this formula in. So d equals okay. So that's the formula, and then what do we want? We want to find the average speed from the time period from t equals 3 to t equals 5. So the average speed is. She told us that it was to calculate it, change in distance. Okay, so we're going to go from t equals 3 to t equals 5. So one of these is really easy. Which one do we know right off the bat? Delta D or delta T? Delta D? Delta T is what? 2. 5 minus 3 is, you don't even have to do the subtraction, you know. From 3 to 5 means a change in time of 2. But formally, it'd be 5 minus 3. Okay, so we know that our change in time is 2. So let's actually graph this and show this. This was what I wanted to do. Okay, so here's this graph of time in seconds since leaving the restaurant on the x-axis, distance from the north of the restaurant on the y quantity. Okay, and so we're talking about a change in time here from 3 to 5. So this is 3 and 5. Okay, so there's a point on the graph for time equals 3, and that point is both that time in seconds and the corresponding distance north of the restaurant in meters. Okay, and similarly at 5, there's a point on the graph here. It was already there, I'm just highlighting it, right? Those points were already there because that's just all points, a bunch of points. And so I'm just highlighting t equals 3, the point, and the point for t equals 5. And so how can I show a change in time of 2? So starting here, a change in time of 2. Up, down, left, or right? To the right. There's our delta t of 2. And so if we want to get the average speed, now we're looking for the corresponding delta d. So from here, up, down, left, or right? up. So we want to find that change in distance. And then our average speed will be that change in distance divided by that change in time. So I've got the change in time of 2. I can just put it into this equation, which is our, and get the corresponding change in distance, right? So if I put 2 into that, 2 is my change in time, it'll crank out the change in distance. Yes? No, this isn't right, because when you put 2 in that equation, what are you telling that equation? What is that 2 about when you put 2 in there? What is the meaning of that 2? Is it a change in time? So what is the 2? So if you put 2 in there, which is it? Is it the change or 2? Well, to you it's the change. But what does that formula think it is? It just thinks that two seconds have gone by since leaving the restaurant, right? It thinks, oh, you mean this 2 right here, t equals 2. So if you plug 2 in there, what do you get? You get, what, 1, okay? 2 is, this makes 8, minus 7 is 1. And that 1 is not, has nothing to do with this change in distance. It's the distance in meters north of the restaurant at 2 seconds. Okay, I'm making a big deal about this because this is a very common mistake that students make. They get the change in time and they say, oh, I can just put it into the distance time formula to get the corresponding change in distance. That's not what that formula does. That formula gives you an actual distance from the restaurant for a given time. So it gives you this 1 here. That's 1 meter north of the restaurant. So if we want to change in distance, we need to go back to our fundamental way of calculating a change in distance, which would be, how do you calculate a change? How do you calculate the change in a quantity in general? Final minus initial. So we need the final distance at 5 seconds and the final the initial distance from 3 seconds. And then what will we do? No, just to get the change in distance. Subtract, right? So we need to get this distance at 5 seconds, which we can get from the formula by, is that 50 minus 7, 43? So this is like D, say D5, minus the distance at 3 seconds, which is, 3 is going to be 9, 18, minus 7, 11. Did I do the math right? This is a really important point, and students miss a lot, so be careful. To get the change in distance, you need the final distance minus the initial distance. Don't take the change in time and plug it in. So this will give us the average speed in that time frame, which is going to be a lot different than the number 1, right? So what is this? It's 43 minutes. Is that 32? Is it 16? What are the units on that? Average speed. Meters per second. Okay, so the average speed of the car starting at 3 seconds to 5 seconds is 16 meters per second. And is that, what is that, a changing speed or a constant speed? It's only one number, so it has to be a constant speed. You get one number. Is it the constant speed that he drove between 3 and 5 seconds? No, he sped up, right? It's a curve, right? He sped up. So that's why we have to make sense of this number. If he sped up and we got this single number, that's where we come back to our principle of average speed. It's a constant speed, equivalent constant speed, to go the same distance, 32 meters, in the same amount of time, 2 seconds. So it's like another person, another car that was just cruising at a constant speed. So what that would be, 16 meters per second would be a line. When we know he sped up, so his graph is a curve. Okay, questions on that? So this is really important stuff. Representing changes on a graph, understanding how to find the change in, say, the y coordinate, the y value quantity, by getting the final value minus the initial. Okay, and then average speed is going to be delta d over delta t, or the constant speed needed to go the same distance in the same amount of time. So we got 16 for that. Let's put that in here. And we said that was meters per second. Okay, so as the number of seconds since Bob began driving increased from 1.5 to 2 seconds, how much does his distance change? So, what was that change in time? What change in time is that? Delta t of 0.5. So we're going to take 0.5 and plug it into this formula to get the change in distance, corresponding change in distance. Right? Okay, so you all should be thinking no. If you're not, then you're not paying attention. Okay? Because I just, that was my soapbox, right, for the last 5 minutes. Okay? Don't do that. So we need what? To get a change in distance, we need final distance minus initial distance. That means get the distance at 1.5 and the distance at 2 and subtract. So the distance at 2 is 1. So the distance final is 1. 1.5, that's not so easy. Let's see, 2.25 times 2, 4.5 minus 7, negative 2.5. Did I do it right? I could have made a mistake. Yes, I did, because that. Oh, I just switched it. Should be 2, 8, 1, distance initial. Oh, so minus negative 2.5, right? Oh, crying out loud. Okay, distance final would be 2 times 2 squared minus 7. Got that right. 2 times 1.5 squared minus 7. Okay, I was right. So the distance at 2 seconds is 1 north. The distance at 1.5 seconds is 2.5 meters south. So that change in distance will be 1 minus negative 2.5, which will be 3.5 meters. Total distance traveled in that time frame. So let's just check the answers on that much, and we'll be done with that. Got all those. Okay, so is he driving? We looked at that graph. Is he driving at a constant rate of change? Is his distance changing at a constant rate with respect to time? No, because if it were, then this graph would be straight line. So let's look at the very last question down here, the multiple choice. It says, so Bob is or is not driving at a constant speed? Is not. He's not because he's traveling in 10-meter increments. No, that has nothing to do with it. So the increments that he's driving in doesn't have anything to do with it. Every 10 meters takes the same amount of time. Every 10 meters takes the same amount of time. What is that talking about? That would be constant rate of change. That you'd have the same change in distance for the same change in time. So that's not right. The ratio of delta D to delta T stays constant. Constant rate of change. The time it takes to go 10 meters is changing. There we go. So now we got this distance of 10 meters. It's going to take a different amount of time to go every 10 meters. That's non-constant rate of change. Okay, so we got those two. Okay, so when you get ready for your quiz and when you take your quiz, the name of the game is applying, knowing, and applying these principles. So this thing that we talked about at the beginning. So the 3 principles of constant rate of change and how we use, especially we use number 2 to build our linear equation. So that's what you are responsible for. As well as always defining your variables well. Okay? Applying, how do you calculate a change, right? Final minus initial. Value of the quantity. So really, even if you've seen linear equations in the past, you really want to force yourself, be deliberate about applying the stuff that we're learning, because it's about analyzing how two quantities change together. It's worlds different than find M, find B, plug in, write the answer, move on. Okay? We really want to think about all this stuff in terms of how two quantities change together. Okay, where are we at? Let's see here.
Question.
Yes, please.
When will the quiz be posted on Blackboard?
Today.
You have a time?
Let's see. When are we out of here? 1:15? 1:21. Okay. Okay, we're gonna do something new. So we're gonna move on here. Next module. So this is, imagine this is a sheet of paper. And I can change the width and length of it. Okay, so I'm going to just do a standard sheet of paper, which is 8.5 by 11. So we make the length 11. Close enough. And then the width 8.5. Okay, so this is showing an 8.5 by 11 sheet of paper. Okay, and then I want to cut squares out of the corners, equal size squares. Okay, and I can choose what size I want. So I can cut small squares like this, or I can cut much bigger squares like this. And I can choose how big those squares are. And so say I'm just going to choose this side right here. And what I'm going to do is I'm going to cut those squares out. And then what happens is it leaves kind of flaps. You can't see it's kind of hard to see the contrast there. Yeah, you can't really see it. But anyway, so you got like this, now the middle rectangle and these flaps that are there, and we're going to fold up the flaps and make a box that doesn't have a top, open top box. Okay, so then I could go back here, start again. Oops. So then I could choose, say, super small squares. Okay, really small squares. I'm going to cut those out. And then fold up those flaps. And when I choose a different size square, I get a much different shaped box now. So this box is a lot wider and flatter, right, for smaller squares. And you saw the bigger squares gave me a tall, kind of more slender box. This is like a fatter and shorter box. Okay. So what this kind of gives us a situation where we can talk about lots and lots of quantities. Okay, lots of quantities we can brainstorm about here. So let's do that. So I have another view of this. Hopefully, let's see. We're in certain module 3 and PowerPoint 1. Paper box. Let's see. Is it this one? Oh, come on. I don't know what it is anymore. Okay, so this is showing the same thing. So it's showing, but kind of two views at once. So if I cut a small corner, I get a flat low box, and as I make the corner, I cut out the corner larger and larger, the box changes, gets taller and more narrow, based on folding those flaps up after you cut the corners out. So what I want you to do is think about as many constant and changing quantities relative to the situation as you can. So get a partner and try to come up with at least 3 constant quantities and then maybe at least 5 changing quantities in this scenario, okay? And then practice your changing quantities, practice writing them out. Practice writing them out with good specificity so you know exactly. We didn't finish yet. Here we go. So what we're saying? We're saying changing. Or let's do some constant quantities first. So what constant quantities might we talk about? Let's write them over here. Okay, who's got a good constant quantity in this situation? Tell me your name. Justin? The length of the resulting box. Is that a constant quantity? Does the length of the resulting box stay constant? So, or can it change? What do you think, Justin? It can change, right? So that's a good one for changing. Let's just start that list too. So he wants the length of resulting box if we're just, so yeah, let's just go ahead and put units on there. So, and let's call that L. So I use script little l to mean the length of the resulting box in inches. Well-defined quantity? Is it a quantity? Is it specific enough? Do we know exactly what it is? And does it have units? Right. Again, keep practicing doing that. Don't just get in that habit and use it to solve problems. So use your attention to the quantities to help you understand and solve problems. So does someone else have a constant quantity they wanted to? Okay, so when you say size, though, specifically what quantity do you want for size? So there's lots of ways to measure the size of something, right? So we want to be specific. What specifically about the size do you want to talk about? The width? Width, sure. Width of the original paper. Is that constant? You guys like it? Yeah, the width of the original paper. And even as you cut out, do you see that that is maintained? Even as you cut out squares, can you see that still that width of that original paper is still there, right? So it's like from here to here, call it, say, big W, okay, big W for width. Do you see how that stays constant even as you cut out different size squares? And what was that value of W, that constant value of W? 8.5, right? 8.5. Okay. Another one. Yes? The length of the original paper. What's that value? So, do you see in this picture where that would be? So like, no matter where you cut the squares out from here, that's all the way to here, call it, say, capital L. That's going to stay constant. What was that value? $11, right. So yeah, I had 10.95 in my thing, so I was going for 11 there. So 8.5 by 11 sheet of paper. So those dimensions, 8.5, the width, 11, the length, stay constant no matter how you cut the squares. All right, so other changing quantities. Yes, sir?
I use W to define width.
Okay, the width of what?
The width of the resulting box.
Good. So let's use like a lowercase or script W. Width of the resulting box in inches. Good. Okay. Yes, ma'am.
H equals the height of the box in inches.
Changing or constant?
Changing. I have a question.
Sure.
Would the volume stay the same?
Okay, volume. Good. So what do we think? Let's take a look at it. She wants to know, is the volume of the box going to be constant or changing? Yeah, it sure looks like it's like if I take a really, really small square, it's like going to be so low, we could think of it almost as 0, right? Like I could get that ledge, that height of that box from a really super small square. It's gonna really the volume will get really close to 0, won't it? But if I cut a bigger square, now clearly I've got some positive.
But the base gets smaller.
What's that?
But the base gets smaller. So
That's true.
it gets deeper. So what is the volume?
But this is so. But the base is only so big, right? The base is going to be. It has a limiting size, right? 8.5 by 11. So imagine the base is 8 by 11. It's not going to get any bigger than that, right? But I can make the height as small as I wanted. So that's going to 0, right? So the volume is going to 0 because the base isn't getting infinitely big. It's staying at 8.5 by 11, while I can make the height as small as I want. So that's just a smaller and smaller and smaller volume box for smaller and smaller
I
squares.
just I picture it like a pool. So like if you were to fill that with water,
Mm-hmm.
it'd be a really shallow but like wide pool. But then if you like made it skinnier, it'd be really deep but less of like a surface area, I guess.
What I'm trying to argue though, so what I'm saying is that you can make the height as small as you want. So at that height, you can just keep making it smaller and smaller and smaller with a tinier and tinier and tinier square. That volume is going to keep decreasing because this only has so big to get, right?
Okay.
So this is like virtually a 0 volume box at the beginning with a really small height. It's virtually 0. In fact, so it's like you can't hardly put any water in there. But then here you could certainly put a lot more water in than just laying it flat on the sheet. A lot more water will fit there. And then similarly at the end here, look at this. Is that volume the same as this one? Doesn't that look a lot smaller than this? So the volume is definitely changing. Okay, yeah.
What about
Surface area of, sure. Is that changing or constant? Yeah, but we keep cutting away more and more of the paper, so that surface area has to do what? Yeah, getting bigger or smaller? It's going to get smaller because if we keep cutting out a bigger and bigger square, we're taking more and more paper away. So the resulting box has less surface area. Yeah, so definitely changing. So we can call that, say S. And what's the units on surface area? Inches? Inches squared, right? So inches squared would be inches squared. Anyone dying to share one more changing quantity? Yes, sir.
Maybe P equals perimeter of box in inches.
Okay. So so we want to be specific. What exactly do you mean by perimeter? So perimeter of what?
Of the resulting box.
Okay, so the reason that's a little bit problematic is because it's a 3-dimensional thing. Perimeter is like the distance around the outside of a 2-dimensional shape.
Okay.
So as long as you specify,
Perimeter at the top of the
yeah, say the perimeter around the top of the box. That's good. So perimeter around the top of the box.
Would there be any other constant quantities?
Yeah, we could think of a couple more maybe. Anyone got another constant quantity? So she said the size of the original sheet. What's another way to measure the size of the original sheet? So we got the width and length. What's another measure of size? Area. So you can say the area of the original sheet. Other comments, questions, additions? Yeah. Oh, the number of squares. Nice. Number of squares that you cut out is 4. Yeah. Number of squares cut out. In this, the way that I set up the situation, it's always 4. Yeah, nice. Okay, so we want to focus on, so the volume we said for sure. So the volume of the resulting box. And what would the units for the volume of the resulting box be? Inches cubed, right? It's kind of like asking how many cubes of 1 inch by 1 inch by 1 inch could fit into the box. So it's like measuring that amount of space by 1 inch cubes, right? By 1 inch cubes. Okay, so we want to focus on, let's focus on, there's still one more changing quantity that's important. It's kind of something that happens before we get to the box. So what's one more changing quantity that we have just from the beginning? Yeah. Right, so those square cutouts. And so we're going to use x for that. So that would be, say, this dimension right here. From there to there is x. Also from there to there is x. And how does x then relate to the height of the resulting box? So we say x is the length of the cutout, and then we have this one, height of the box in inches. How do those two quantities relate? X and h, the height of the box. What's that?
X equals.
You want x? Does x equal h? So whatever he's saying whatever side square you cut out, when you fold up those flaps, that's going to be the height of the box. You see that? Yeah, that's true. Right? Because you imagine folding this flap up, and now that's going to be your height. From there to there will be the height. So they're different quantities because one's this length of this cutout, the other's the height of the box, but they always have the same value. Okay, so x will always equal h in this setup, but they are different quantities because they're talking about different things, but they turn out to have the same value. Okay, so can we write the length of the resulting box? So that length of that resulting box here, we're going to focus on length of the resulting box, volume of the resulting box, and this x. I guess I never wrote x down, but x is the side of the square cutout. So I'm going to erase one here. There we go. So surface area was a great one. I just need some room, so don't feel sad if it was yours. Okay, so x equals the side length of the square cutout. In inches. Okay, so I'm going to focus on volume of the resulting box. I want to focus on the length of the resulting box in inches and the side length of the square cutout. So of all the variables that we defined, which one would this be right here? What would that be right there? That's supposed to be straight, okay? Measuring that dimension. Which of those variables would correspond to that dimension that I just drew? Yeah. L. Right now I'm just asking about like which one of these. But yes, you're on the right track. You're just a little bit ahead. But so which one of these variables correspond with that right there? Little l, right? And where do you see little l in this page? So how could I also define little l on this over here? From where to where? So is it from this down here at the bottom up here to down at the top? So from here up to, yeah, so that same dimension is right here. That's that same L that will be the length of the box. Okay? So, and we said big L was 11, right? 11 inches. And big W, the original width, was 8.5 inches. So remember our formulas, writing one quantity in terms of another. I want to write L in terms of, or just a formula for L. So it'll be up to you to figure out what it's in terms of. So a formula for L. How would you calculate this value, the resulting length of the box? So what can we use to come up with this length right here? How about somebody new? What was your name in the blue again? Yeah, Shannon. What do you think? Little L. Can we come up with a formula to compute that changing length of that box? So it's kind of based on this, the original length of the paper, right? Is it longer or shorter than the original length of the paper? By how much, right? So we could start with 11, and we could say how much shorter is it than the original length of the paper? Uh-huh. So like here is x. So what do you think? She said 11 minus x. You're going to need two of them, right? You need one up on top too. So if we take that whole distance, this whole distance is our 11, and we take off this x for this square, and take off this x for this square, it leaves us with the length of the final box, so 11 minus 2x. All right, so what is that? That's L in terms of x. Remember formulas, L in terms of x. Okay, so now using that same, I'm going to keep taking roll, using that same pattern, I want you to come up with a V in terms of x. So in general, let's just get a general form for the volume of this box, so we all know. Volume equals, of a rectangular box, length times width times height, okay? So if, that would be V in terms of L and W and H. That's pretty cumbersome, right? So instead, can you write V in terms only in terms of X? Using the same kind of strategy here that you wrote L in terms of X. Now we want to write V in terms of X. So V equals what? So I'm going to finish taking roll. You can work on this a little bit. So if you get it, so some of you just can say it right now. Others cannot. So if you just know it right off the bat, don't tell your neighbor, okay? So we need everyone the chance to think and figure it out for themselves. So if you want to help your neighbor, then listen to them and ask them a question. Don't just tell them the answer, okay? Some have it already, some need some time. So let's give everyone the time to figure it out for themselves, okay? V in terms of X. Don't just tell people the answer. Okay, Vince, you're the lucky winner. Did you come up with this? Vince, yeah. B in terms of x. No? Okay. Let's see. Somebody new. How about, is it Nada? Nada? How'd it go, Nada? So that's the height. So you want the height times w times h. Okay, good. So we got the height is 11 minus 2x. So then what if we're going to do times w times h, then we need w in terms of x. Did you get that? So if we do 11 minus 2x times w times h, it's still not only in terms of x. So there's an x in there, but we want only x's. We want only x's. So now we got to get w in terms of h. Yep, it's going to be the same thing looking at this way. Here's our width of the final box. And it's going to be the 8.5 less an x on this side and an x on this side. Okay, then what about h? We said h was x. So look, we just got v in terms solely of x. So given a square cutout, what does this formula do? All you need to know is the size of the square cutout, and that formula gives you what your volume will be at the end. So we are having a conversation about, does the volume change or stay the same? So let's put in a volume of, so put in x equals 0.5 inches. So just we can convince ourselves. 0.5 inches, and say x equals 2.5 inches. And calculate the two volumes that you get for those two squares. So x equals 0.5 inches, x equals 2.5 inches, and let's convince ourselves that the volume is truly changing, okay? Because that was a question we had. So can I erase everything on the screen?
Yeah.
So let's do that here. So I'll just write down the formula now. So volume equals length, 11 minus 2x. So this formula, it's not about, okay, I'm going to memorize this formula now. The ability to build it is the thing we want. So that's what we want to be able to do, is given any situation, to be able to build a formula like this. Memorizing that is not the goal. Okay, so that's just to show us what it is. So we want 11 minus, what did I say, 0.5? 2 times 0.5. Okay, times 8.5 minus 2 times 0.5 times 0.5. 37.5 cubic inches. And now let's do 2.5. So I'm going to change all these 0.5s to 2. To 2.5. 52.5. So we see at the beginning anyway, as you increase that side of the square cutout, that volume's going up. That volume is going up from 37.5 when the cutout is 0.5 to 52.5 when the cutout is 2.5 inches. Okay, this is a good stopping point. So for Thursday, you're going to have web work. It's not posted yet. It will be this afternoon. You got your quiz. Okay? The quiz is posted. Study, prepare for the quiz. Work it out beforehand. It's posted. Everyone should get A's on the quiz, right?
No, Thursday.
The quiz is on Thursday. Yeah.